Welcome back. So I promised you at the end of the last video that I was going to show you a way that was, I don't know if better is the right word, but a way that's a little bit more straightforward to understand how we get these energy levels out of the system. And I should be clear that although this way is better, I sort of have to know that the other way exists in order to trust this way. And that is to say, I need to believe, or I need to understand, or I need to accept the fact that the harmonic oscillator has enough boundary conditions to give us quantized states. And it's actually a good thing to know what the energy levels of those quantized states are going into the analysis that we're about to do. But if you know that, then this analysis really makes thinking about those energy states a little bit more straightforward. So the first thing I'm going to do is I'm going to take a look at a commutator, not because it's a hard one, or not because it's really central to the problem. We're going to use it in the problem, but it's one that uses a trick that we've talked about before, and so I want to make sure to show you explicitly how to do this commutator, and that is the commutator of the position and the momentum. Now, if I'm going to do this in the position basis, it actually makes sense, as we've done a couple of times before, to use a test state as a tool for trying to figure out what this commutator is. And when I do that, I'm sorry for moving it, then I end up with something that looks like, well, I have the integral over dx, right? That's because I have to decompose that state onto the eigenstates of the position operator. I then have my x operator, p operator, and I'm going to write them down in the position basis, right? So this is x times minus I h bar d by dx minus I h bar d by dx of x, and then of course times the wave function, and then I have my eigenstates at the end. And the key to why I wanted to do it this way is in noticing when I start to do these terms out, right? So now I'm going to take my wave function, I'm going to pull it in. My first term actually doesn't look too surprising, minus I h bar x d psi dx. But my second term has a d by dx that's now going to hit both the x and the psi, which means that I have to use the product rule, right? So I have, sorry, I forgot a minus sign here, right? I have plus I h bar. I'll do the d by dx of x first. Well, d by dx is just 1, so I have a psi. And then I also have a let's see, plus I h bar x d psi dx, again from the product rule. And you'll see what happened here is now this term cancels with this term. I'm left with I h bar times psi. Well, I can now take the state right out, right? Because the integral dx psi x is just my state psi, and I end up with I h bar times my state. And that's how I get to this famous conclusion that the commutator of x and p is equal to I h bar. And that's just going to be something I'm going to use, but I figured it was a good opportunity to walk you through it because using a test state to calculate a commutator is something that often gives us a little bit of anxiety. Anyway, okay, commutator of x and p is I h bar. Keep that in mind. So let's go back to my expression for the harmonic oscillator Hamiltonian. Here I have p squared over 2m plus 1/2 m omega squared x squared, right? And I mentioned in the last video that we already start to love this thing because it's got a p squared and it's got an x squared, and it looks like it has a lot of symmetries, right? It looks like it has some interesting it looks like it has some interesting physics in it because it's the only potential where I have just an x squared, right? If I had anything else, it would be a different type of potential. And so it's the only way that x and p sort of contribute to the potential in the same way. So I'm going to pull out some constants. I'm going to pull out an h bar omega, motivated primarily by the fact that I know that the energy eigenstates are going to have energies that are in units of h bar omega, and then I have everything else. And so now I have something, again, that goes like x squared plus p squared, right, with some units. And if we think back to, when have I seen this sort of thing before? Well, I saw it when I was actually looking at the total angular momentum operator, right? I had things that looked like sx plus sy, right? And I related those to some s squared, right? So seeing these two things added as squares gives me some memories for other operators that I've been working with. Again, I want to make sure those memories are something that we're holding on to. And that is why I'm going to define two new operators, A and A dagger, that are going to be made up of one copy of X and P, right? And I want you again to remember when we did this for the spin operators and we talked about S plus and S minus, I took SX and SY and I either added them or subtracted them, and one of them had an I on them, right? And by doing that, I could come up with combinations of Sx, Sy that gave me Sx squared plus Sy squared. The algebra here is identical. If I define A and A dagger in this way, I can define A dagger A to be a combination that looks like M omega over 2H bar, and then the two terms that I wanted from the previous slide, right? These are the two terms that I get when I rearrange the harmonic oscillator Hamiltonian. And the other thing that I get is the commutator of X and P, which we know is just IH bar, and right, we did that work a couple of minutes ago. And so I end up with the thing that I want, and then something that's just a constant, right? And the I's even give me a -1, right? Like it's just a thing, right? It's just a number. And that's amazing, right? Truly amazing. The M omega is even, it blows our mind, right? How wonderful this expression is going to be, because it allows me to recognize exactly what I want to rewrite my Hamiltonian in terms of the A and A dagger operators, right? The same way that, again, I wrote my S squared Hamiltonian as only ladder operators, or only S plus and S minus, and SZ. And so now I can totally rewrite my Hamiltonian in what looks like a magic form where H is equal to H bar omega, A dagger A, plus a half. Right? And again, that plus a half comes almost magically out of the fact that H bar over M omega times M omega over H bar over 2 is just a half, right? And that half was so confusing to us on the last video because it seemed to come out of nowhere, right? That there was this extra 1/2 that I got in all of my states. And I think that we at least can use the algebra to see why whatever I get out of this operator, I'm going to add a half to it. And that's going to give me that extra half an H bar omega that I need in order to get the right energy eigenvalues. To do that, though, or to see this, I'm going to have to do a couple of commutators. I'm going to do them fast, right, because we've done enough commutators today. AA dagger is just AA dagger minus A dagger A. I can use the replacement of the Hamiltonian, and I get that actually this commutator is just equal to 1, right? This should, again, remind you of S plus, S, blah, blah, blah. I've said it enough. I won't say it again. I can also do the commutator of H in one of these operators, right? So if I take the commutator of H in A dagger, I get this big old long expression, right? Luckily, some things cancel, and I'm left with something that just has another commutator in it, the commutator of A dagger A. Well, the commutator of A dagger A is just minus the commutator of A dagger. Oh, that should have a minus sign there, right? And so, nope, I'm sorry, this is a mistake, right? So I have A dagger, so that goes there, that goes there, that goes there, and this is a plus sign. This is that rare case when two sign errors make it right. This is correct, okay? The commutator of the Hamiltonian with A dagger is A dagger H bar omega, okay? Which means that H A dagger minus A dagger H is equal to A dagger H bar omega. Okay, now these are commutators. But what they give us are they give us equations, right? They give us relationships that I can use now to try to understand the problem. Would I expect you to come up with these out of nowhere? Absolutely not, right? It requires, apropos of understanding what the final answer is going to be, before I realize what commutators are going to make it most convenient. Even when I was writing up these notes, right, to talk to you today, I wrote down a number of different commutators before I got the efficient path towards the answer. Okay, so you can't be afraid to calculate a couple of wrong commutators. Or I shouldn't say even wrong, you should calculate a couple of useless commutators, because for every couple of useless commutators that you find, there's going to be a good commutator that's going to help you finish the problem. But this relationship that I got from doing all of these commutators is going to be really helpful to me in a minute. Because if I start with the assumption that I have an eigenstate of the Hamiltonian. Specifically, I'm going to have the eigenstate n, which, as we know from the last video, has energy h bar omega n plus a half. If I start with that state, and I understand that that state is an eigenvector of the Hamiltonian, I can act a dagger on that state and find out whether or not that state is an eigenvector of the Hamiltonian. So let me find out by taking h and acting it on the state a dagger n, right? Well, the relationship I came up with on the last slide to replace h a dagger gives me these terms in blue on the right-hand side. Well, I know hn and is an eigen, right? That's hello, right there, right? This next term, well, that's just a constant, right? And it's got my a dagger in it. And now I see that, look at this. The state, a dagger n, is also an eigenstate of the Hamiltonian, but its energy is just bigger by 1 h bar omega, right? And therefore, it must be proportional to just the next state, right? If n is an eigenstate with that energy, then a dagger n is an eigenstate with 1 more h bar omega energy, right? It is an eigenstate. It's just at a higher energy eigenstate. It's in fact the n plus 1 eigenstate. Or I should say carefully, it's proportional to the n plus 1 eigenstate, because eigenvectors have to be, eigenvectors have an unknown constant of proportionality, and we'll write down what that is in a second. So the a dagger operator takes in an n, gives me an n plus 1. Well, the a operator takes in an n, gives me an n minus 1. And so these are just raising and lowering operators. Okay? And I have to always wonder why they chose the dagger to be the raising operator. And this also comes from the fact that the first time I saw this, I was actually taking it in Britain, and they called them the creation and annihilation operators. And I always thought that the annihilation operator would be the one that has the dagger on it, because it feels very Romeo and Juliet to me or something. Anyway, so this is one of two times in this video where I'm going to say I remember it because what I think is right is wrong, right? That a dagger doesn't destroy it; it actually lifts it up, right? And a is the one that brings it down. And the constant of proportionality then is, I can actually show you what it's going to be, right? We could use the process of having an unknown one and plugging it into things and making blah, blah, blah. Let me just give you what it is, and then I'll convince you of it. That a dagger acting on n is going to be the square root of n plus 1 times n plus 1. A acting on n is going to be the square root of n times n minus 1. And for these, both of how I remember it, again, this is the thing that I get wrong, which is why I have to think about it. In either case, right, whether you're raising a state or lowering a state, there's going to be one of those two states that's bigger. And that's the number that goes inside the square root. Okay? So, and for some reason, I always think it's the other one, and then I get it wrong. And anyway, the number inside the square root corresponds to the larger eigenstate. But if I do this and I plug it into my Hamiltonian, I find out that a is going to give me the square root of n minus 1. A dagger is going to give me back my n state, but another square root of n, right? And that's n, square root of n times square root of n gives me n. And that immediately, I don't know why I just erased that. That immediately, I want to put it in a nice big thing, gives me my eigenvalue of the energy. Okay? So your take-home messages are, there's a raising operator. There's a lowering operator. They combine to make the Hamiltonian. And this is a way to think about the energy basis of the problem. Okay? I hope that was at least a little bit more.